Good morning. I'm Sharanyan, Srikanthan. Sandhya, Dwarkadas, and Shen are my advisors at the University of Rochester. Today, I'm here to talk about a recent work that focuses on extracting performance from modern multicore systems in a manner that's transparent to application users. It's an important challenge today because modern multicore systems are fairly complex. They share a lot of resources such as caches, on and off chip interconnects, and memory between all the CPUs in that system. And a natural implication of this sharing is there can be a lot of contention, and if this contention is not managed properly, it can result to a lot of performance degradation. Another aspect of modern multicore machines is non-uniform access latencies, and non-uniform access latencies would result in threads incurring widely variable costs for accessing data and for communicating between each other. What this results in is in order to be able to get the best performance from your hardware, an application or a user using that platform has to be aware of the system, its topologies, the tasks that are running with it, and so on. And our research focuses on extracting the same performance from the hardware, but in a very transparent way that the user does not have to worry about all these aspects. So we look at the first aspect of modern multicore systems, that is resource sharing. In this figure, we have a dual socket machine with a CPU with multiple CPUs, and each CPU sharing its private level of cache, having its private level of cache. But beyond this private level of cache, all the other resources such as the last level cache, the inter-process interconnect, the memory bandwidth, and the memory capacity are all shared between all the CPUs. So clearly the sharing can be quite bad when multiple threads of the same application or multiple applications contend for these resources, and has to be managed in a clever way. The second aspect that we've touched upon is the non-uniform access latencies. In this figure, we can see that for a CPU to access data that's in its private cache, it takes a few cycles. For it to access something in its last level cache, it takes a few tens of cycles. And for it to access something that's local but in the DRAM, it takes on the order of 100 cycles. The second that the processor has to access something that's remote to it and go to a remote DRAM, it takes almost twice the time in a couple of 100 cycles. And it gets even worse if it tries to access something in a remote cache, because the access takes in the order of magnitude of a few hundred cycles as opposed to a few tens of cycles, which would be the access latency inside the same socket. So it's very, very clear that both NUMA issues where you access memory in a remote RAM and the access latencies for a remote cache, all of them are important in achieving good performance. An example case here shows the impact of replacement on data sharing. In this example, we have two tasks running on two different sockets sharing data. And for them to share data, the only way is to use the inter-process interconnect, which we've seen is fairly expensive. So a better way to run these two tasks would be to co-locate them on the same socket, but this won't be the solution for any bunch of threads, because putting them on the same socket essentially means that you're not using the resource on the second socket. So this is a challenge that has been studied and looked at with quite extensive effort. We look at some of the related work that are most relevant to us. Tam et al. Study an address sampling-based approach to identify and infer data sharing between threads. This approach would work very well for certain for certain applications and access characteristics, but as an implementation, it still has, it is costly and it's very specific to certain processors. Tang et al. Study a way to leverage performance counters to identify resource sharing, but they do not consider the aspect of non-uniform access latencies. And a paper that we saw yesterday by Lepers et al. Studied the maximization of non-uniform memory bandwidth that's available to an asymmetric machine, but in their research, they do not talk about the aspects of sharing a shared cache. And our approach is that of a sharing-aware mapper. We call it SAM. In using SAM, we are able to identify and separate bottlenecks in the system that arise due to data sharing from resource contention using performance counters for parallel and mixed workloads. And we are able to use this information along with the non-uniformity of the system to be able to migrate and mitigate these bottlenecks to achieve better performance. So SAM is a three-pronged approach, the first part of which is a monitoring one. We'll look at that in more detail. For the first part of SAM, we need to read performance counters periodically in order to analyze application behaviors. we look at 4 important metrics that, according to us, dictate the state of the system and help us derive information on the bottlenecks on the system. The first of which is inter-socket coherence activity. This is the activity, these are the data accesses that go to a remote cache and are served by a remote cache. As we've seen before, these are pretty expensive in terms of latency. Intra-socket coherence activity are those accesses that are served by the coherence protocol inside the same socket. In our machines, this is the most optimum way when 2 tasks want to communicate with each other. So tasks that have higher intra-socket coherence activity are well placed. We also monitor for remote memory accesses to identify tasks that actually access memory in a remote node so that we can place it appropriately to localize its accesses. And we use the local memory accesses, the aggregate information of local memory accesses on a particular socket to estimate the pressure on the memory subsystem to serve data. In order to monitor these 4 metrics, we need 8 performance counters in our hardware because our platform does not inherently give us these statistics. So we indirectly and approximately infer these information from the performance counters, the details of which is discussed in the paper in fair detail. So the second part of SAM is to analyze and infer from the current system state if we have any bottlenecks or not. And for this, we need to compare the system state with certain pre-characterized thresholds that we arrive at by using micro-benchmarks that we craft. So the first thresholds that we arrive at is related to coherence activity. We have a micro-benchmark that has 2 threads that ping-pong data between each other. And we pin the 2 threads of this micro-benchmark across 2 sockets and then colocate them and observe the speedup that we get on colocating them. So the graph shows exactly the same, and we mark a point which is 5% speedup that is obtained upon collocating the threads as being a significant point, and we mark that as a threshold for coherence activity. So the second thing that we're interested in when your memory bandwidth is saturated. And for this, we not only need to know the capacity of the memory bandwidth, but we also need to know something that's called the row buffer hit ratio of the application, because that is a primary factor in how much bandwidth the application can even access. So here we have a micro benchmark that has 2 variants. One has high row buffer hit ratio, the other has a low row buffer hit ratio. We compare the bandwidth that's actually available to that application, and we can see that for lower thread counts, the difference between the bandwidths is quite large. However, because we are interested in flagging bottlenecks, which is associated with saturation, the saturation bottlenecks between these 2 applications is only about 10%. So we take the more conservative estimate of the low row buffer hit ratio as our estimate for thresholds. So the third part of SAM is a decision-making logic in which we take remedial actions by manipulating process-to-processor affinities. Decision-making logic of SAM prioritizes the reduction of inter-socket coherence activity over the reduction of remote memory accesses, which then has a higher priority compared to balancing bandwidth. So in order to achieve these goals, as per the priorities, we need to move tasks around. SAM prefers to move tasks onto idle cores, if there are any, or at least to CPU, or swap our more prioritized tasks with CPU-bound tasks. We define CPU-bound tasks as those that do not contend for resources or share a lot of data. If we do not find either of these 2 opportunities and we still have a need to reduce inter-socket coherence activity, we do make the trade-off of moving a memory-bound application. We know this is not an ideal migration, so we call them reluctant migrations, and we note them and find the earliest point in the future at which we can reverse these migrations to reduce the remote memory accesses that could have been a byproduct of such migrations. But at no cost do we actually move tasks that have intra-socket coherence activity, because that is going to violate our most priority to reduce inter-socket coherence. Here's a working example of how SAM would go about deciding which tasks map onto cores. Here we have 4 tasks and an exponential 2^4 ways of mapping tasks to cores. We have tasks T1 and T3 that share data, and T2 and T4 that access memory, but they are accessing memory that's remote to their sockets. we find in our various experimentations that this is actually something that we encounter a lot when we use native Linux to test our programs. So the first step that SAM takes is that it realizes that T1 and T3 share data and collocates them on the same socket, thereby alleviating some pressure from the interprocessor interconnect. The second step that it does is that it recognizes the remote accesses from T1 and T2 and it rectifies them, therefore fully taking all the stress out from the interprocessor interconnect and localizing all access to their respective sockets. And then it looks at any opportunity to balance memory bandwidth, and in this case there aren't any, so that this is the final configuration that SAM would settle at. So here we can actually analyze and find out that this is the most optimum solution for these bunch of applications. And one curious thing to note that is here we have one socket running 3 threads and another socket running 1. This is not a traditionally load balanced system in the sense that there are different number of threads running on different number of cores, but this does happen to be the optimum solution. So if you were to use Linux that distributes load, you'll never get to this solution. You'll always have some bottleneck or the other. So for more discussion of our experimental results, we use an Intel Ivy Bridge dual socket machine with 10 physical cores, 2 hyperthreads, and 25 megabytes of last level cache. We built SAM over Fedora Linux 19 with a kernel number of 3.14. We use several benchmarks to evaluate SAM, starting from our micro benchmarks that we've used for thresholding, then spec CPU benchmarks that are either CPU intensive or memory intensive. We use some of the parsec benchmarks that are parallel and have data sharing, but they're relatively light when it compares to some of our other benchmarks that are more focused on the emerging workloads that we see in fields like machine learning, computer vision, etc. So these emerging workloads have very strong data sharing, and they have very dynamic behavior in the application. The application behavior changes in time. There are threads that are created and destroyed, and there needs to be a lot of dynamic decisions that need to be taken on the fly. SAM is implemented on top of Linux. Linux chooses, given a pool of tasks, which tasks run at the same time, and SAM decides where these tasks run. So it's a thread to core mapping that's done using manipulation of processor affinities. So initially we start by analyzing how SAM performs for standalone applications. For standalone applications, we compare SAM and Linux with respect to what we call as the best static schedule, where we exhaustively search the entire space and find out for which thread to core mapping we get the best performance. And what we can see straight away is that SAM performs just as good as the best static mapping because it's able to identify the application characteristics. And in some cases, it's actually able to perform better. And it performs better than a best static schedule because it is able to dynamically adapt to the needs of the application. Overall, SAM performs 21% faster than Linux. And in some cases, it actually performs just as good as Linux because you can see Linux performs just as good as you can. There are two types of workloads for which this happens. One is the workloads are CPU bound. If your workloads are CPU bound, thread to core mapping really does not do a lot to increase performance. And second, if your workload is entirely memory intensive. If your workload is entirely memory intensive, the ideal thing to do would be to distribute the load across sockets, and this is what SAM would do. And this is also Linux's static heuristic, so SAM and Linux get almost the same speed up in such cases. Moving on to workloads, mixed workloads, where we put several applications of different characteristics and natures together to see how SAM does. In this figure, we see SAM's performance with respect to default Linux, and the blue bars, they might not be visible very clearly, are whiskers that show the discrepancy between multiple applications in the same workload. More detailed analysis into these workloads is in the paper, but overall SAM performs 16% faster than Linux, and again, in some cases, it's only as fast as Linux because the applications cannot be accelerated anymore. It has a peak performance of 36% more than Linux for some workloads. And in addition to improving performance, SAM also reduces the disparity of speedups across different applications in these workloads because it's able to analyze what each workload needs and reduce their contention. So in addition to improving performance, we do reduce the performance disparity between the different applications in the same workload. a bit more of detailed insights into why we see these performance, because we can see from figure B that most of the inter-socket coherence activity has been detected and reduced in case of SAM. And we also see increase in a lot of the intra-socket coherence activity to show that we have localized most of the task communication as much as we can. So and we can also see from the off-chip traffic that for almost all cases, the off-chip traffic is reduced, but in some cases, SAM actually has more off-chip traffic than Linux. It might sound like it's a bad result, but off-chip traffic essentially includes both the memory accesses and the usage of inter-process interconnect. And in these cases where the off-chip traffic is higher compared to Linux, SAM actually achieves this because of balancing memory bandwidth utilization better and getting more from the memory subsystem. So a closer look into the overheads of SAM. Overall, it has an overhead of just less than 1% for the 40-core machine that we have. Almost all of the overhead is due to the performance counter monitoring, which is run at every tick. It's a constant time overhead. And the second part of SAM, which is the data consolidation and identification of bottlenecks part, that takes about a couple of orders of magnitude lesser than the performance counter reading, and it scales linearly with the number of processors. The third part of SAM, which is the decision-making logic that actually move tasks around based on the different bottlenecks that we've observed, is actually O(n) squared with the number of processors, but in our case, for our implementation, it takes negligible time. Our SAM's implementation is centralized because the O(n) squared complexity does not dominate. And if for a much higher amount of processing cores it does, we would have to make it distributed, and that's a part of future work. So conclusions, performance counters give sufficient information to be able to identify different bottlenecks that arise due to data sharing or resource contention. SAM is able to use the information from the performance counters to improve application performance by minimizing inter-socket coherence, by minimizing remote accesses, and by maximizing the memory bandwidth utilization. In addition to improving performance, it's also able to reduce performance disparity. And as a part of future work, we would want to go into the benefits of hyperthreading, because hyperthreading goes a step ahead of sharing a last level cache, because multiple cores now share even a smaller cache. So it might have implications for different applications that have different access patterns and sharing patterns. So thank you.
I actually had a question, and you cited the paper that was presented earlier in ATC, and I was wondering if you had any thoughts on how an analysis of the asymmetry in those interconnects might affect your work. And I know you did all of your work on Intel chips, and it turns out AMD is a lot different. So I wonder if you had some thoughts on that. So
yeah, I do. So for the AMD machines, the asymmetry is a big factor. But if you look at their research is a lot about, you have a NUMA node, and you move the NUMA node depending on how much it communicates with others to the fastest possible links. You can draw an analogy here, because here you have certain processors that communicate faster with each other, certain processors that communicate slower with each other. It's a matter of understanding that you have these various ways of communicating, some of which is faster, some of which is slower, and you map processing modules that communicate faster with each other closer to where it is faster. So from that point of view, I think it sort of goes towards the same goal. But I think one aspect of their research that could be very beneficial to us is they actually move memory. They move memory based on who's accessing it and so on. And AMD actually, interestingly, gives you information on which node is communicating how much with which other node. So if we have that information, I think it would be very beneficial for us to even move remote, move the memory that's accessed remotely, instead of always having to move data, and even make better trade-offs that don't have certain performance implications.
Great, thanks.
Thanks.
All right, let's thank our speaker.